Okay, welcome back, everyone. We're going to make a big jump here back to thinking about statistical mechanics. And in particular, when we were talking about the classical mechanics of Chapter 5, we were mostly relying on actually experimental measurements to predict things, instead of experimental measurements of things like enthalpy and Gibbs free energy and so on. But it would be very nice if we could actually go back to understanding these systems from a modeling standpoint, from a quantum mechanical picture, and then try and predict things like the enthalpy, the Gibbs free energy, things like that. And so to do that, we need to pick up a couple of useful tools. And the first one of those is the one we'll talk about today, which is the Boltzmann factor. All right, so let's start with our imagining a system. And in particular, our system is some small system over here. It doesn't necessarily matter what it is, but for the sake of our discussion today, we're going to make our system a hydrogen atom. And we're going to let that system interact and come to thermal equilibrium with a large reservoir, which has a temperature T. So the system can exchange energy with the reservoir, but for the moment we're going to limit ourselves to just exchange of energies. We're not going to allow, for instance, particle exchange between the system and our reservoir. I guess technically we are allowing volume changes, but as we'll see here, volume changes in the case of the hydrogen atom, at least for much of the states of the hydrogen atom, aren't really a significant effect thermodynamically. So our system here is going to be something small. In this case, it's a hydrogen atom, but it doesn't have to be. It could be anything that is small compared to the large reservoir over here to which it's attached. And the reservoir is basically the environment around our system. You can think of it as the entire universe if you want to be explicitly pedantic, but basically it's the nearby region of the environment, which is considered much larger than the system, and therefore much less responsive to exchanges of energy and so on for the system. They don't affect the reservoir dramatically. All right, so in this situation, we're going to let this figure be a hydrogen atom, and if we remember our, let's make this a little bit bigger, basic discussion of the hydrogen atom. There's a ground state down here with quantum number n equals 1, and then at the n equals 2 stage, there are a number of not only the sort of the so-called s orbitals, but also the p orbitals. And then as we go up to n equals 3, there's the s and the p and the d orbitals and so on. So at each level of energy, the primary quantum number for energy is this n, and so the ground state has an energy of 16 or 13.6 eV below the ionization point, and the n equals 2 state has a energy level of minus 3.4 eV below the ionization level, and so on. All right, so when we have these states which have different quantum numbers but effectively the same energy, then we call those degenerate states. And in this particular case, there is one of the s states, but there are 3 of the p states, 3 of the p orbitals, and so the degeneracy of the n equals 2 state would be 4, that there are 4 states up here with the n equals 2. Now technically, actually, there are, if you take into account the spin angular momentum of the electron, there are actually twice as many states. So there's in fact 2 spin states down here in the n equals 1, 2 spin states in the n equals 2s orbitals, and 6 spin states available in the p orbitals. We'll see here that it doesn't really matter, at least to the discussion we're having today, whether it's 2, 2, and 6 or 1, 1, and 3. The point being that the n equals 2 state is has 4 times as many states as the n equals 1 state. And what we're going to try and develop is a understanding of the probability of finding our atom in any particular given state. And in general, that probability is going to depend on all of the available states. So to begin with, we're just going to actually consider the probability of the relative probability of finding a system at a different in a different state. So the relative probability of finding, for instance, the atom up here in the 2s state as opposed to down here in the 1s state. So we're going to ask ourselves, what is the relative probability? All right, so let's give ourselves some nomenclature. So we're going to, again, the hydrogen atom here is just an example. We're going to consider whatever system it is that we're talking about has at least 2 well-defined quantum states, 2 well-defined states here, and we're going to label those states. We're going to label them S1 and S2. And those states are going to have energies E1 and E2, so that, wow, I'm not sure, is it actually more legible with the lights off? Well, that's pretty dim now. Is there a happy medium here with the light levels? All right, we'll just turn them all the way back on. All right. E1 and E2. Wow, that is really bright. We'll do our best. All right, let's roll with it. And the probability of being in each state we'll label here as probability 1, or the probability of being in state 1, and the probability of being in state 2, like so. And remember, the fundamental assumption of statistical mechanics was that for an isolated system, all of the microstates are equally probable. Well, the thing is, our system, our atom, is not, in fact, an isolated system. We just said that our atom is connected to a reservoir. But we could consider the entire reservoir and system as our isolated system. And then it's a matter of, well, we then have to count up the multiplicity of the reservoir plus atom in each of the atom's 2 states. So we could talk about the multiplicity of the reservoir when when our system is in state 1, and we would call that omega r state 1. So this is the multiplicity of the reservoir when the atom is at state 1, and similarly the multiplicity of the reservoir when the atom is in state 2 we could label like so. And obviously if the atom is in state 1 there's only one of those, and so the total multiplicity of our reservoir plus system would just be the multiplicity of the reservoir for this one given state. So all the ways that we could arrange the reservoir when the atom is in state 1, this is going to be the total number of states for our reservoir plus system in this configuration, and similarly with this. So that the probability then of being in state 2 divided by the probability of being in state 1. So in other words, the relative probability is just going to be the ratio of those two metallicities. The ratio of the reservoir, or sorry, those two multiplicities, the multiplicity of the reservoir when we're in state 2 divided by the multiplicity of the reservoir when we're in state 1. Let's turn this into a discussion about entropy, because entropy is a more common way of thinking about things thermodynamically. So let's convert our omegas here into entropies. The relationship there is the fundamental definition of entropy, that the entropy is K times the logarithm of multiplicity, which if we then divide by K, so S over K is the log of multiplicity, and therefore that the multiplicity would be e to the S over K. So we could replace each of these with that, so that the ratio of our probability at S2 and the probability of being in state 1 is thus the e to the entropy of the reservoir at state 2 minus the entropy of the reservoir at state 1 over Planck's constant K. Now, since the reservoir is very, very much larger than our system, any exchange of entropy, any change in the entropy of our reservoir is going to be small compared to the total entropy of the reservoir as we exchange energy with the system, so that we can consider basically the delta S here as a ds, and then use the definition, or the thermodynamic identity. We can say that ds of the reservoir, well, that's going to be 1 over temperature times du of the reservoir plus p dv of the reservoir minus mu dn of the reservoir. Now, our system is not allowed to exchange particles with the reservoir, which means that the dn of the reservoir isn't changing, and that second term goes away. And for the most part, especially if we're talking a hydrogen atom, the change in the volume as we go from one hydrogen state to another hydrogen state, this change in the volume tends to be very, very much smaller than the change in the energy, so that the PDR or PDV term also tends to be very small. It's not always the case for all systems that you could ignore this, but in a vast majority of systems, and a very great number of systems where we're talking about quantum mechanical energy levels and things like that, very often the PDV term is also ignorable. And we're certainly going to ignore it here in our hydrogen atom analysis. So in this case, then, the only thing that's relevant is the change in the reservoir's energy, the exchange of energy between our atom and its environment, so that we can write down this delta S of our reservoir as 1 over T times the change in the energy of our reservoir. So the energy of the reservoir when we're in state 2 minus the energy of the reservoir when our atom is in state 1. Now notice we're talking about the entropy of the reservoir, the temperature of the reservoir, although the temperature is also the temperature of our atom if they are in thermal equilibrium, the temperature of our system if they are in thermal equilibrium, and the energies of the reservoir when the system is in state 1 or the system is in state 2. So we're characterizing the reservoir by the state of the system. And since the system is the only thing the reservoir is interacting with, that's still a unique label. And in particular, since the energy exchange is with the atom, between the atom and the system, the change in the energy of the reservoir when we go from state 1 to state 2 must be the opposite of the change in the energy of our atom. So it must be the opposite of the energy at state 2 minus the energy at state 1, where these energies are talking about the energy of the system itself, in this case our atom, whereas these are talking about the thermal energy of our reservoir. So if we replace the temperature or the energy difference of the reservoir here with the energy difference of our atom, then we can say then that the delta S of our reservoir is equal to minus the energy at state 2 minus the energy at state 1 divided by the temperature. And thus that the ratio of probabilities of being in state 2 versus being in state 1 is going to be e to the minus the energy difference between state 2 and state 1 divided by kT. Or we could write this as e to the minus energy of state 2 over kT divided by e to the minus energy of state 1 divided by kT. And notice then that the ratio of the probabilities of being in state 2 and state 1 is just the ratio of these two factors here, both of the form e to the minus energy of a given state divided by kT. And this is what we call the Boltzmann factor. And it turns out that this is very, very useful tool. We can see here that obviously the probabilities must be proportional to the Boltzmann factors. Let's make this explicit. Let's rewrite this equation here, gathering all of the S2 stuff on the left and all of the S1 stuff on the right. So the probability of being in state 2 divided by e to the minus energy of state 2 over kT. That's got to equal the probability of being in state 1 divided by e to the minus energy of state 1 over kT. Everything over here depends on state 2. Everything over here depends on state 1. And indeed, the labeling of the states is completely arbitrary here. We could label anything state 2 and anything else state 1. This must be true for all states. In other words, this must be some constant. And indeed, we label that constant of proportionality, or that constant 1 over z. And if we do so, we find that the probability then of being in a state S must be 1 over z, whatever that constant is, times e to the minus energy of that state over kT. So in other words, it's the probability of being in state S is just this factor 1 over z times the Boltzmann factor for that state. And this we call the Boltzmann distribution. And it turns out that the Boltzmann distribution is quite possibly the most monumentally useful thing in all of statistical mechanics. This is an incredibly useful equation, an incredibly useful idea, because it allows us to describe the probability of a particular of a thermal system being in a particular state, as long as we can evaluate the discrete energy states. So any quantum system where you can identify or evaluate all of the different energy eigenstates, you can evaluate the thermal probability distribution for being in any of those energy eigenstates. And this is an incredibly powerful tool for making predictions about the probabilistic behavior of any kind of quantum system or any kind of a thermal system. Let's look a little bit. Let's look a little bit at the details here of this thermal system, or of this Boltzmann distribution. When the this kT term, we've run into this before, and this kT is basically it's a characteristic thermal energy associated with a temperature T. So any system with at a temperature T is going to have a characteristic thermal energy of the order of kT. So kT, that kind of represents the average thermal energy in the ambient environment in which our system finds itself. So it's the kind of scale of energies that our system is going to be finding available to it. And if a particular state has an energy well above the ambient thermal energy kT, then this Boltzmann factor has an exponential suppression of the probabilities, right? So if you have a temperature, or if you have an energy in your eigenstate that's way above the thermal energy of your environment, then that eigenstate is going to be sparsely populated. The probability of finding yourself in that state is going to be very, very low. Whereas if we take the energy level to be very, very low, much lower than KT, then we don't have that suppression of the probability distribution. This 1 over z factor, the normalization factor, if you will, for our probability distribution, the constant out in the front. Indeed, normalization is the accurate term because that's how we're going to that's how we're going to calculate it. If you sum up the probabilities of being in a state S over all of the possible states of our system, so in this case over all of the possible energy states of the hydrogen atom, if you sum up that probability, all right, which means we have to sum up 1 over z times the Boltzmann factor e to the minus energy of a state over kt. Well, again, this z comes out in front because it's just a constant, so it can come out of the sum there. So this is 1 over z times the sum of all of the possible, or of the Boltzmann factors of all of the possible states of our system, and that's the sum of all the probabilities. Well, our system has to be in some state. Our atom has to exist in one of the states, and so the sum of the probability of being in a state, in a particular state, must always sum up to 1, because this is a proper probability. The state can only exist in one, the system exists in at least one state. Well, it exists in one state, and so if we add up all of the probabilities, those probabilities must add up to 1. And this then allows us to say that the factor z there is just the sum of all of the Boltzmann factors for our system, and this z is what we call the partition function. Now, it's a little weird we call it a function because I just said previously that it's in fact a constant. Well, it is a constant for a given temperature. Notice that since the Boltzmann distribution depends on temperature, therefore so must also the sum of all the Boltzmann distributions for a given system. The energy states, those are states of the quantum mechanical system itself. The atom, the energy states of the hydrogen atom doesn't change depending on the temperature of the environment the hydrogen atom finds itself in. But the partition function for a hydrogen atom in thermal equilibrium with a reservoir of temperature T, that absolutely will be a function of temperature. And so we call this constant of this normalization constant, we call it the partition function. And the partition function is the sum of all possible Boltzmann factors for our system. So if you want to calculate the relative probabilities or the total probability of a system being in any particular state, all you have to know is all of the energy levels and all of the states that are possible in that particular system. In other words, you have to be able to make a diagram like this. This is a truncated diagram, obviously, because it doesn't show any of the states between n equals 4 and n equals infinity, and there are a very, very large number of states up there at the top. Between n equals 4 and n equals infinity, there's in fact an infinite number of bound states for the hydrogen atom. So in principle, this partition function would be an infinite sum, and that can be a difficulty if you have large finite temperature partition functions to calculate. So in practice, calculating partition functions can be tricky. Often they have to be done numerically. Although you can make pretty decent approximations, for instance, at low temperatures, because again, at low temperatures, if we look back over here, if the temperature is low, then that means that the energy levels for most of our hydrogen, or most of our system, so if we're talking about the low temperature distribution of hydrogen, well, there's a great big gap between n equals 1 and n equals 2 here, for instance. And if the ambient thermal energy is way down here, if kT is way down here somewhere, then the 10 eV gap between n equals 1 and n equals 2 might be quite large relative to that ground state. And so most of these upper levels won't be very populated, and it might be possible to get pretty close to evaluating the partition function by only evaluating the first 3 or 4 levels. You may not have to go all the way to infinity if you have relatively modest temperatures. Indeed, at very, very low temperature, the partition function is essentially 1. And if you look at this, this partition function is essentially a probability weighted count of all of the states. And so roughly speaking, what the partition function represents is the number, if you want to think of it that way, the number of accessible states of a system at a given temperature. So as the at the low temperature limit, you tend to have partition functions that basically have a value of 1. And as you increase the temperature, the partition function increases as well. And it's essentially a probability weighted average of, or a probability weighted sum of the count of states, and therefore basically something like the number of available states for a particular system at a given temperature. Well, let's take our hydrogen atom and imagine it in a physically interesting or physically realistic context. The context of, say, for instance, a hydrogen atom in the sun's atmosphere, right? So the ground state, or the difference between the ground state of hydrogen and the first excited state of hydrogen, so the n equals 1 to n equals 2 state, that's a delta E from 2 to 1 of 10.2 electron volts. Again, that's a pretty big jump between the ground state of hydrogen and the first excited state of hydrogen. And so the relative probability of being in one of those n equals 2 states versus the relative probability of being in an n equal 1 state. Well, if you just looked at a particular n equals 2 state and a particular n equals 1 state, we're going to come back to the degeneracy of the n equals 2 states here in just a moment. Well, that's just going to be the ratio of those Boltzmann factors. So that's going to be, again, e to the minus delta E from 2 to 1 over kT. kT in this case, well, that's 8.6 10 to the minus 5 eV per Kelvin. In this case, it's convenient to use the eV per Kelvin version of Boltzmann's constant, and the ambient temperature, at least at the surface of the sun, is about 5,800 Kelvin. So KT is something like half an EV, whereas the delta E here is more like 10 EV. So we're relatively suppressed up here at the n equals 2 states, and indeed e to the minus 10.2 EV divided by a half an EV, that gives us a relative probability of being in a single n equals 2 state versus the probability of being in a single n equals 1 state as roughly 1.4 times 10 to the minus 9. So for every billion atoms, you'd have 1.4 of them in the n equals 2 state. Now let's take a look at the degeneracy, because in fact there is one n equals 2 s state, but there are 3 n equals 2 p states. So in other words, there are actually 4 times as many of these as there are those. And so the actual probability of being in any of the n equals 2 states, which in this case depends on changes to the quantum number L, versus being in the n equals 1 state, and there's only one of those ground states, that's actually 4 times larger, so it's actually 5.6 times 10 to the minus 9. Still heavily suppressed by the fact that the ambient energy, thermal energy in the sun's atmosphere is way below the energy level difference between the first excited state and the ground state. These occupation probabilities mean that most of the hydrogen atoms in the surface of our sun, by a factor of nearly 1 in a billion, or a few in a billion, are going to be in the ground state. So most of, only in a billion hydrogen atoms in the surface of the sun, only a tiny handful of them are going to be in that first excited state. And this is important because the transitions that we can see in the atmosphere of the sun, if we look at a spectrum of the sun, there are these dark lines that occur in the spectrum of the sun. Here, for instance, is, well, this is not the spectrum of our sun, but in your textbook, this is the spectrum of a star very much like our sun. And we can see here there are these dark these dark absorption line features in the spectrum of that star. Those dark absorption lines happen when we have, so here's the n equals 1, here's the n equals 2, and so this is the s states, these are the 3 p states, and then n equals 3 is up here, and there's s states and p states and d states. The transitions that we can see in optical spectra are the transitions between the n equals 2 and the n equals 3, the so-called Balmer transitions of hydrogen. The ones that go like this, well, actually they would go technically like this and like that, or like this. But the transitions between n equals 3 and n equals 2, and if you have a photon that comes along with exactly the energy of between the 2 and the 3, then it has a high probability of being absorbed if there's an atom there in an n equals 2 state. So the number of atoms in the n equals 2 states has a strong effect on the strength of hydrogen absorption lines in stellar spectra. And the hydrogen absorption lines in the spectra of the sun are actually relatively weak. Here we can see spectra of different stars running from relatively cool stars on the bottom with a surface temperature of about 3,000 Kelvin to relatively hot stars, the hottest stars being 40 or 50,000 Kelvin on their surface. And we can see along here, these are the locations of the Balmer series line. So this is H alpha and H beta and H gamma, H delta. These correspond to transitions from the n equals 3 and above states, n equals 4, n equals 5, those kinds of transitions back down into the n equals 2 state. In emission or in absorption, they would be transmissions, or they would be transitions from the n equals 2 state to n equals 3 for hydrogen alpha, n equals 4 for hydrogen beta, n equals 5 for Balmer gamma, n equals 6 for Balmer delta, and so on. And what we can see here is that these hydrogen transmissions are strongest in here when the stellar temperature is roughly 10,000 Kelvin. Now that's interesting because if we go back to asking ourselves what's the Boltzmann factor going to look like at 10,000 Kelvin, well, when we're at 10,000 Kelvin, then we still have that the delta E over KT, well, that's going to be 10.2 eV to get up to the n equals 2 state, divided by, again, 8.6, 10 to the minus 5 EVs per Kelvin, and at 10 to the 4 kelvins, we're still only at a factor of about 12. It was about 20 or so for the sun. We're down to about 12, but we're still then going to have Boltzmann factors of e to the minus 12. So still pretty heavily suppressed, even though the strength of the hydrogen features is peaking there. And one might ask, why is it that the hydrogen features don't peak at higher temperatures? Why not 40,000 Kelvin? Why not the hottest stars? Why do the hottest stars not show strong hydrogen absorption features? Well, to understand that, let's go back to the hydrogen diagram here and look at the energy level structure. By the time we get KT up to the point where it's of the same order of being at the second energy level, then we're actually 3/4 of the way to ionizing the hydrogen atom itself. And what we'll find is that when we look at, for instance, the Maxwell distribution, we look at the available energy level, or the distribution of kinetic energies for ideal gases as a function of temperature. By the time the KT energy in our thermal gas has gotten to the point where it's of the order 1 with this 10 eV difference between the ground state and the first excited state, then there's a tail of particles that are way above the 13.6 eV ionization energy needed to just ionize hydrogen entirely. So the reason, in fact, that the absorption lines of hydrogen peak at about 10,000 Kelvin and then die off as you go to hotter is not because of the population by the Boltzmann factor, but actually because ionization of the atom becomes of hydrogen becomes a dominant force. That once you start to get close to the energy of that first excited state, you've got most of the energy needed to ionize the hydrogen away. And so the strength of the hydrogen absorption actually drops off because ionized hydrogen can't absorb any light at all. There's no electron there to excite anymore. All right, So that's where we're going to leave here today, and we will pick up next week and use the Boltzmann distribution to analyze some thermal systems.